Yes, good morning all of you. This is Jasminder Kaur and I'm here to teach nature of singularities. So let's start with the assignment 3, that is of expected examples. Very important one. Before starting the example, we have to revise some of the remarks which are very helpful in almost all the examples based on discussing the nature of the singularities. The first one is, the limit point of the sequence of poles of function fz is a non-isolated essential singularity. Many times, most of the times, this remark is very helpful in almost all the examples. Second, if fz has an isolated essential singularity at z equal to z0, then fz comes arbitrarily close to every complex value in each deleted neighborhood of z0. This is nothing but your causality-Weierstrass theorem. Just take this as your result. Third one is, if limit z tends to a fz does not exist, then a means the point at where you take the limit, and if by taking the limit at that point on fz it does not exist, then that point a is essential singularity of fz. Or if principal part of fz contains infinite number of terms, then a is isolated essential singularity. Isolated means the one and the only one singularity, right, in the finite part of the plane. Fourth one is, a function fz at infinity has isolated singularity if and only if f of 1 by z has an isolated singularity at z equal to 0. That means, if you are having your function at infinity, that is having isolated singularity at infinity, then if you take z instead of z, if you take 1 over z, then it must has an isolated singularity at z equal to 0. That means your 0 is what? Nothing but 1 over infinity, right? We are just changing z to 1 by z. So infinity is get changed to 1 by z, that is 1 by infinity, which is equal to 0. So for if fz, the point is z equal to infinity has isolated singularity. So for 1 by f of 1 by z, it has an isolated singularity at z equal to 0. Fifth, how to check the order of the poles? This is the formula for that. Limit z tends to a z minus a the power n fz. If this limit does not equal to 0 or infinity, then this power n is the order of the pole. And if this n is equal to 1, that means if the power is 1, then the order of the pole is 1, which is a simple pole. Sixth one is, e raised to the power 2n pi iota is equal to 1 for all n belonging to the integers. If you apply the Euler's formula here, that is cos of 2n pi plus iota sine of 2n pi, that will be equal to 1 if you solve this, right? And for odd powers, this is minus 1 for all n belonging to integers. We will use these two in the examples, or one of these two in our examples. Now the example 1. What kind of singularity have the function fz equal to 1 minus e the power z over 1 plus e the power z at z equal to infinity? First of all, we have to find the poles of the fz. And we also know that whenever I am having z equal to infinity, so the first thing comes in my mind about the limit point of the poles, because I know that if z is the limit point of the sequence of the poles, then your z is isolated essential, non-isolated essential singularity at z equal to infinity. So first of all, I am finding the poles. Now the poles of the fz are given by taking the denominator equal to 0. So this is 1 plus e the power z equal to 0. From here, I get e the power z equal to minus 1. And just now in the remark we have read that whenever e the power z equal to minus 1, what is my z? The z is, yes, for odd powers, 2n plus 1 pi iota, right? So z equal to 2n plus 1 pi iota, these are my poles, the sequence of poles, right, for all n belonging to the integers. Now if you look over here, as n tends to infinity, z is also tending to infinity. If these are your sequence of poles, what is the limit point of this sequence? We can find the limit point of this sequence by taking n tends to infinity, right? And we are getting z tends to infinity for that. So as n tends to infinity, z tends to infinity. So z is a non-isolated essential singularity at infinity, because here z becomes the limit point of these sequence of poles, right? So z is non-isolated essential singularity at infinity from your remark 1. Now to check the order, limit z, this is the formula for checking the order. This limit should not equal to 0 or infinity. Now here my point A is what? 2n plus 1 pi iota, right? So limit z tends to A, that is 2n plus 1 pi iota. Z minus A will be z minus this A into f of z. 1 minus e the power z over 1 plus e the power z. Now what I am going to do is, I am taking the numerator separately and the denominator, the part of the denominator separately. I take the limit as z tends to 2n plus 1 pi iota, taking numerator here and taking this part z minus 2n plus 1 pi iota with this denominator 1 plus e the power z. Limit z tends to 2n plus 1 pi iota. Now what is this limit? This is, put z equal to 2n plus 1 pi iota over here. This is 1 minus e the power 2n plus 1 pi iota, and for here, because it is 0 by 0 form, so this is, you take the by applying the L'Hopital's rule, I'm differentiating the numerator and denominator. So this is 1 over e raised to the power 2n plus 1 pi iota, right? And this is 1 minus, this is nothing but your minus 1. This is also minus 1. So this answer is minus 2, which is not equal to 0 or infinity. Because it is not equal to 0 and infinity, that means fz has simple pole at z equal to 2n plus 1 pi iota, because here power is 1. I have taken power to be 1. So for power 1, I am getting my limit not equal to 0 and infinity. That means I am having the simple pole of order 1. Second example, this is very important. Prove that fz equal to e the power 1 by z has an isolated essential singularity at z equal to 0. Now if I take z to be equal to x for all x reals, I will just check the limit. Limit x tends to 0 plus, it is given that you have to check for z equal to 0. So if I take the right hand limit on this, e the power 1 by x, what I am getting? This is 1 by 0, that is infinity. Taking the left hand limit, this is e raised to power 1 by x, the negative power. So this is your 0, because 1 over infinity is 0. So therefore, limit x tends to 0, e the power 1 by x does not exist. And whenever at the point where the limit does not exist, that point is essential singularity. From the remark you have revised. Hence z equal to 0 is an essential singularity of fz. Now whether this singularity is isolated or not, let's check. Since z equal to 0 is the only singularity of fz in the finite part of the plane, so therefore fz is analytic in every deleted neighborhood of z equal to 0. If this is your 0 point and this is the neighborhood, at all the points except z equal to 0, because z equal to 0 is your singularity. So except this singularity, at all the points the function is analytic, right? The function is analytic. So singularity at z equal to 0 is isolated, because z equal to 0 is the only singularity. Now the other way to prove this is e to the power 1 by z is equal to 1 plus 1 by z plus 1 over z square plus 1 over z cube up to so on. Now taking the limit z tends to 0, e to the power 1 by z is equal to limit z tends to 0, 1 plus 1 by z plus 1 over z square, so on. So this is equal to 1 plus infinity plus infinity plus infinity up to infinite times. As it has infinite terms, then singularity is essential. And if there are finite number of terms, then we say that it is a pole. So z equal to 0 is your isolated essential singularity. Third example, this is also very important. Show that e to the power z has an isolated essential singularity at z equal to infinity. Now let f of z equal to e to the power z. I have to reciprocate it, right? Now because the nature of the singularity of the function fz at z equal to infinity will be same as that of the function f1 by t. Just reciprocate it. If f of z is at z equal to infinity, I will take f of 1 by t at t equal to 0. I have taken here z to be as 1 over t. So for z equal to infinity, I am having t equal to 0. Now taking the limit t tends to 0 on f of 1 by t, that means limit t tends to 0 on e raised to the power 1 by t. This is equal to 1 plus 1 by t plus 1 over t square up to so on. Again, I am having infinite number of terms here, that is equal to 1 plus infinity, so on. Infinite number of terms. Now the principal part of f of 1 by t is what? This is your principal part, right? That is 1 by t plus 1 by t square plus 1 over t cube up to infinite number of terms. Now because it consists of infinite number of terms, so t equal to 0 is an isolated essential singularity of e raised to power 1 by t, and consequently z equal to infinity is an isolated essential singularity. So z equal to infinity is isolated essential singularity. Here ends up the examples. Alright, thank you so much. Have a nice day.